All right, welcome everyone, and thank you so much for coming for today's talk, Eyes in the Sky, Viewing Still Creek through Remote Sensing. My name is Connolly, and I am the Stewardship Program Manager for Still Creek Art Society. Our organization is dedicated to restoring habitat in the Still Creek Watershed and creating community and rectifying a neighborhood through both arts and environmental projects. Today and every day, Stillman likes to recognize that we operate on the unceded and ancestral lands of the Musqueam, Squamish, and Tsleil-Waututh peoples, the original stewards of the land. Our Shedding Light talks aim to increase the community's connection with nature through learning from local projects and science, led by artists and students and scientists. I'd like to thank our funders at TV Friends of the Environment Foundation, Habitat Trust Fund Conservation, and Vancouver's Greenest City Grant. These talks and many of our stewardship events are all due to their funding in the face of life. Just a quick few housekeeping notes before we get started. There is a sign-in sheet just at the table with snacks. That helps us report back to funders on who came and helps us continue running these events. And also the bathrooms outside, the public ones are locked, but we do have access to our private restroom. Clea is just sitting by the door, so if you need the bathroom at any point, just talk to her and she'll walk you through and get you where you need to go. And now I'll introduce today's speaker, which is Liam Irwin. Liam is foremost an avid lover of all things nature and is passionate about conservation. From his undergraduate degree in conservation, where he studied stream invertebrates, to his master's, where he began to deep dive into geomatics. He is passionate about all things he does. Liam is currently in his final year at UBC at the Integrated Remote Sensing Studio, and his studies focus on the use of remote sensing in Canadian forest management and hopes to improve management. Well, you're not here to listen to me drone on.
Great. Well, thanks everybody for coming out on this Wednesday night. Really appreciate it. Today, I'm going to try to teach you as much as you want to learn about remote sensing and drones and LiDAR. I've kind of tried to spin this with a Still Creek lens. I don't work personally in Still Creek, so I've just kind of brought some examples of things we do elsewhere, and we can talk about how they could apply to Still Creek. I'm happy to take questions during the talk, and at the end, I'll have some time for questions. And then after I'm done talking, we can take a look at some of this cool tech that's over there on the table. Unfortunately, it's dark, raining, and we're in a restricted airspace, so we can't fly the big drone, but I'll turn it on and you'll get about 10% of the experience. But anyway, without further ado, can I just see a show of hands? How many people have heard about remote sensing before? Okay, that's fantastic. So about 60, 70% of you. And I assume you all have heard the word LiDAR before as well, maybe? Okay, cool. So I'm going to introduce remote sensing to those of you who have never heard about it before and explain a couple basic concepts. So it might kind of start out a bit heavy. If you can feel free to tune out, and there'll be pretty pictures later. But if you are keen to learn, I'll try to teach you some of the basics about remote sensing. We'll talk about satellite remote sensing, which is kind of the last 50, 60 years, what we focused on. And then we'll get into LiDAR and finish with talks about drones. So what is remote sensing? Remote sensing is simply the acquisition of information about objects without making contact with them. So if you take a picture of your cat, that is remote sensing. You store that on your phone. Your cat is a brown cat. It is this big. Typically, when we talk about it from kind of an environmental lens, we're talking about using cameras and sensors on aircraft, both remotely piloted or drones, manned aircraft or planes, and satellites. And remote sensing is really amazing because it allows us to cover and assess really large areas and to do so without disturbing whatever object we're interested in. If it's a forest, we don't have to go in the forest. We can observe it from above without making actual contact. So there's two major groups of kind of remote sensing data sources. There's ones that we call passive, and you can think about these as basically cameras. So all of these kind of sensors are measuring light that's reflected from the sun. The sun is super bright, if you didn't realize. It shines light on the Earth, which comes millions of kilometers. That light hits the objects on the surface of the Earth and reflect back to our satellite or our drone or airplane. And those cameras on the platform, we call it, are able to capture passive information. So you can think about it just like a camera, and Landsat is the key one we'll talk about today. And then some other sensors are actually active. So they're actually emitting energy and then measuring it as it comes back to the sensor. And we'll get more into the details about how that works. So first, I want to start by talking about this idea of spectral reflectance, which is basically a fancy way of saying color. So every surface on the Earth has a different spectral signature. It reflects light differently. And so a simple way that you can think about this is a ripe tomato is bright red. That's because it reflects more red light than blue or green light. Our eyes are, you can think about them as cameras, but they can only see visible light. So red, green, and blue light. But luckily we can build cameras to measure all sorts of different kinds of light, not just the light that our eyes are constrained in seeing. And so getting a little bit sciencey here, maybe you remember this from high school science. This is the electromagnetic spectrum. And so basically there's radio waves and microwaves and infrared rays and visible light, ultraviolet, X-rays, and gamma rays. So there's all these sorts of wavelengths of light bouncing around our world. Our eyes and most animals can only see this very small range we call visible light. That everything you've ever seen in your life has been visible light. Some animals can see slightly into the near infrared. That's why cats and other things can see in the dark. If you have like a security camera on your house, it'll actually shine infrared light over the surface and illuminate it, which is why you can see in the dark with those cameras, but you can't see that light with your eyes. So keep this concept of the electromagnetic spectrum in mind when we talk about this stuff. And remember that all the different objects on Earth have different characteristics in how they reflect light, not only in the visible that we see, but beyond the visible in all these different wavelengths. And so forgive my graph here on the right. The y-axis or up and down here is basically how bright something is. And the x-axis here is the wavelength. So I'll just walk you through this a little bit. 0.4 to 0.8, this is the visible light that we see. And so if you just look at this green line here, you can see it has a big bump right around 0.6 micrometers. And this is green, basically. So here's red, here's green, here's blue. And so this vegetation appears green, just like the tomato appeared red because it emitted more red, reflected more red light than other colors. Vegetation appears green because it reflects more green than red or blue. That's thanks to chlorophyll, if you really care. But you'll notice some other interesting things on this graph, all these other kind of surfaces that we might expect to see on the Earth. We have snow and ice and clouds. We know those are bright white, right? They're reflecting lots of red, lots of green, lots of blue. When we get all that light, it looks white to us. But they also have all these things going on here in the near infrared and infrared wavelengths. And we can use specialized cameras on satellites or on drones or on aircraft to basically take advantage of all these differences that we can see in land cover surfaces. So hopefully that makes a bit of sense. Remember, all objects on the Earth emit light differently, and we can basically study those differences and use them to understand what's happening in the landscape. And we do so mostly through the help of hundreds and hundreds of satellites that are orbiting the Earth every single day. Some of these you might recognize, some of them you might not. These are just Earth observation satellites, so these aren't GPS, these aren't telecommunication satellites, these are just satellites with cameras or sensors that are taking pictures of the world every single day. And so the one I'm going to focus on today is called Landsat. Has anybody heard of Landsat before? Yeah, a few of you. So the Landsat program is the longest continuous record of the Earth's surface. We have 52 years of coverage, and Landsat passes every point on the Earth every 16 days. So we have an incredible archive of photos stretching back over 50 years, capturing photos essentially of the Earth, not only in visible, but also in many other wavelengths of light. And we can do some really incredible things thanks to this archive. This has been a huge effort to keep funding for these kind of programs going forward. And NASA has done a very good job of keeping the data consistent over those 54 years. So we can compare an image from the 1980s to an image that was captured yesterday, and we can look at the differences between them and use them to do some pretty cool things. Another really important thing about Landsat is in 2008, the US government made it freely available for people to use. And ever since that has happened, the use of this kind of data has just skyrocketed. Landsat is, they try to, like, with these big government programs, they try to put a dollar on how much benefit it's brought to society. Landsat is the second highest benefit of any satellite system other than GPS, which you can kind of imagine. It's hard to beat GPS, it's pretty incredible. And yeah, it covers a wide portion, not just RGB, it goes into all those different wavelengths. So here is Canada since 1984. And we've done some very fancy things to take all the Landsat imagery from 1984 and basically look at how land cover is changing across the entire country. And we do this at a 30-meter pixel size. So every 30 meters in Canada, you can zoom in, you can look at any year, and you can see what land cover is on that. Is it forest? Is it a plain? Is it water? Is it ice? And when you do this, you can start to see some really interesting things, especially if we look up in the center in the north of Canada. Does anybody have an idea what these might be? They're big wildfires. Up in the north, there's no fire suppression. Fires are a very natural part of the boreal ecosystem, and you can see them just burning away. And those pixels are going from our green class, which is coniferous forest, to our shrub class. So they're burning down essentially. And I'll just zoom into some more closer examples. Here we're in Manitoba now, in the north. On the left, you can see the Landsat imagery. And then on the right, you can see we've colored it by the year that the area has changed. So this goes from 1985 in pink to 2011 in dark. And so you can see how those fires appear on the landscape. We can then detect them thanks to this really dense archive of images. And we can know exactly what's burning, when it's burning, even though there's no people anywhere close to here. We can't get helicopters or aircraft anywhere near there, but we can build up this extremely useful data set that can tell us how much is the forest burning, which is really important for especially for the federal government that has the mandate to monitor a country as big as Canada. We can zoom into another example here in Alberta. That been working? Oh, spoilers.
On one of the previous maps, what was the big white space above the river?
Let's see, Phil. On this one or the one before?
That right here, the large white space.
This area? This is
down below.
Oh yeah, so we've basically clipped this to anywhere that has forest. So this is the agricultural area in the prairies, and this is the tree line. Cool. So this is produced by the Canadian Forest Service. They only have to monitor Canada's forested area, which is only, several million square kilometers. So they like to cut out those small areas to lighten the load on them a little bit. Any other questions about this? Great. Okay, let's see if my Alberta video wants to play. Cannot play media. Sounds like it can't play. That's okay. Okay, so here is some imagery from another satellite called Sentinel, which is a European one. And this just shows you every week from 2016 to 2024 what Vancouver looks like. And here I'm just displaying visible light, RGB, but you can imagine there's many other wavelengths we could do to look at the changes. So you can see, summertime now. You even see some smoke and haze come in. I've filtered out most of the really cloudy images because the problem with Vancouver is, you well know, there's a lot of clouds, so we don't get a whole lot of images. But yeah, you don't see a lot of change when you look at kind of this level, but when you apply it across the whole, there's our snow. When you apply it across the whole country or a large landscape, you can really start to see some interesting patterns. And here is our beautiful Renfrew Ravine. So you can see in the fall, the leaves almost go away. They're turning yellow, they're brown, we get a bit of snow. And remember, this kind of data exists from 1984 all the way to today. And Landsat 9 is the latest satellite. It was just launched 2 years ago. It has, I believe, a 20-year mission length. So we're really set up well to continue that really valuable archive. And hopefully this just gives you some idea of how valuable it is. But you might also notice, Renfrew Ravine, we don't go to a whole lot of detail, right? It looks blurry. It's not blurry, it's just every pixel on the image is 30 meters, right? So we can't get in much finer than that. Okay, shifting gears. That's optical remote sensing. That's cameras on satellites, on aircraft, and on drones. We're going to now switch to a little bit of explanation about active remote sensing. And I like to start with this kind of silly gif of a bat echolocating, because I think it's helpful as an analogy. So bats fly at night. They can't see very well, but they can make ultrasonic noises. So ultrasonic meaning that they're higher frequency than we can hear. Sometimes you can hear a little chirping or something. They blast those ultrasonic noises through the air constantly, and they hear the sound wave come back to them. And they can use that time from when they made the call to when they heard it to actually locate their prey, to tell how far away something is, or to fly around a cave in the dark and not hit the walls, right? And so bats can use this kind of technology to pinpoint their prey, to navigate their environment, and the same kind of concept is going to apply to the next thing I'm explaining, which is LiDAR. So LiDAR uses light like a bat uses sound, is how I like to explain it. So the bat in our analogy is now a sensor on a drone or on a plane or on an aircraft, and that sensor is shooting pulses of light millions of times a second. Those pulses of light travel down from the sensor and hit something. So the bat, it's not a bat now, it's not getting bugs. It's just firing millions of pulses of light across a landscape. It could hit a rock, it could hit a twig, it could hit the top of a tree or your house, like you saw when I was playing around with that point cloud. And every single pulse that's fired hits something, comes back to the sensor. Luckily, light travels super fast, as Einstein figured out. There's the speed of light. So essentially, it's instantaneous for any scale on the Earth. So it fires this light. The light comes back, and since we know how long it took from when it emitted that pulse to when it received something, and we know the speed of light, we can turn that into a distance. If that makes sense? So we have a clock, we know the speed of light, we can turn that to a distance. We have GPS on the plane or the aircraft with the satellite, and we have some other fancy things that I won't get into, but basically we know exactly where the laser is, we know exactly when it fired the pulse and received it, and we can use that to build up millions and millions, billions of point measurements across a landscape, which are super useful for a multitude of things that I'll get into in a second. So do we feel like we kind of understand how LiDAR works? Yeah.
What's the resolution of that distance?
Yeah, so it totally depends on how high you're flying. So a LiDAR from a satellite has a very low resolution product. Like it actually does a transect. It doesn't even cover a whole area because it's thousands of meters up in the air. An aircraft kind of gets around 30 to 50 measurements per meter is the unit we use. So if this is a meter, you can imagine that there's going to be about 30 to 50 points within that meter. Those points could be on trees or on the ground. But yeah, the point density is the way we refer to how dense LiDAR is. And when we get to this drone over here, if I fly this low and slow, I can get tens of thousands of points per meter, which I'll show you a little bit what that kind of data looks like. Yeah.
What about like the distance resolution? Like, I'm assuming it's very good in terms of like bouncing off something like 2 meters versus 2.01 meters.
Yeah, so that's like the vertical accuracy. That'll totally depend on what kind of sensor it is. So this one on the drone is relatively cheap. It's only $15,000. Some ones in planes can be millions and millions of dollars, but it's usually within kind of like 1 to 5 centimeters accuracy. Totally depends on a bunch of things. Any other questions? Okay, cool. And then so the result of all these point measurements, millions and billions and trillions of point measurements, is something called a point cloud. And so I have this little image here to try and illustrate what that looks like. Here we're just looking at a two-dimensional cross-section of what LiDAR data looks like. These white are supposed to be trees and ferns, as you can clearly see, and then they're colored by elevation. So the red points are the highest and the blue are the lowest. So the LiDAR is flying above here, boom, 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 pinging off all the branches and all the ground, and it builds up this beautiful point cloud data set, like the one I was scrolling through before the talk started. Yeah.
So in this example, all the white would be inferred data?
Yeah, exactly. The white's kind of like what we would expect to be there, and then the points are what we actually get. That's what LiDAR data looks like. It's a whole bunch of points. They all have, we know the X, the Y, and the Z. We know where they are horizontally and then how high they are off the ground. If that makes sense. Okay, so what do we do with this data? It's obviously cool, it looks cool. It's super high resolution, but how do we turn all those millions of measurements into something useful? That is kind of the big problem, and that's where a lot of the research that we do comes in. So we can use, in our focus, we use vegetation or LiDAR for two main things, looking at terrain and looking at vegetation. So that's what I'm going to focus on today, but you know, you can do archaeology, you can do so many other things with LiDAR data that I'm not going to cover in this talk. But hopefully you get some ideas going. So we can measure vegetation, we can measure the flow of water, we can collect LiDAR data multiple times and then look at changes. How are the trees growing? Are they dying? You can even look at how buildings are coming and going across the landscape. The city of Vancouver flies LiDAR about every 5 years over the entire area, and Metro Vancouver just flew it in 2022. So we start to build up these data sets over time. Hopefully you can see from our Landsat example how useful this kind of data is when you collect it over time. And in my opinion, LiDAR is even more useful than the images that we can get from our satellites. So Still Creek, let me orient you a little bit. We are right around here, I believe. Here's the Renfrew Ravine. It's colored by elevation, so you can see it slopes down as we're heading down Still Creek. Here's the community center. Here's that cross section. That previous one I had was just an example of what we'd expect the data to look like. This is what it really looks like. So here's the Renfrew Ravine, nice and flat. And then thankfully, we get a really nice steep ravine, which is probably the reason that it's here today and probably the reason that we're all here today, because they couldn't develop it. And we can turn that LiDAR data into some really cool things. So here I just have some imagery just for reference. We can look at each pixel in the area and say, what's the highest point? And that's how we kind of infer tree height. So here you can see bright white is the highest thing and black is the lowest thing. So you can see all the little houses, but also all the tree canopy within the Renfrew Ravine. Because we have this 3D information, we can actually strip away all the trees and just look at the vegetation, or the terrain, excuse me. I have a 3D printed model of the Renfrew Ravine terrain, which you can all take a look at later. But yeah, this is the super useful part of LiDAR, right? We get information super dense about the vegetation and about the terrain that's beneath the vegetation. A camera on a satellite like Landsat will only ever give you information from the top of the forest where it can actually see sunlight reflecting back to it. But LiDAR is really powerful because it can get through the tree canopy and tell you information about the ground beneath it. And we can build vegetation models looking at the surface. We can strip away those trees and just look at the terrain beneath it. So this is basically a very similar thing to what I showed at the ravine, but just in 3D and spinning, so it's more fancy. And we can take that terrain model across the landscape and look at slope. And even though this is just showing you slope, our minds already start to pick out features, right? You can see the rivers, you can see the roads. So remote sensing science is all about trying to pull that information out of this super rich data so we can give our managers or the government or whoever our stakeholders are something to use on their end. So I'm going to go through some examples focused around streams because Still Creek is a forested stream. So this is kind of the most relevant thing I can think of. And a lot of our work has focused on how can we use LiDAR to monitor fish habitat. LiDAR is often flown over forested areas for industry. They want to know how much wood is there, how big the trees are essentially. So in our lab, we've looked for a lot of kind of added value that we can get from that same LiDAR data set that the industry has collected to give us information on things like caribou habitat or fish habitat. We've done some work with marbled murrelets on the coast. So there's a lot of additional information that companies aren't going to use the LiDAR data for, and we try to pull those out. So in this example, you can see our terrain model. We can essentially take a giant theoretical bucket of water and pour it all over that terrain model and see where the water is flowing on the landscape. And that gives us our stream network. Once we have our stream network, we can look at things like how steep is the stream. Once we know how steep the stream is and how wide it is, we can say, is it actually accessible for salmon or fish? We can classify it using the government's arbitrary stream classes. We can look at the vegetation around the stream to see how tall the trees are and how much cover there is over that riparian ecosystem. And this kind of information can tell our managers a lot about the state of the watersheds and the protection that they require. We've done some recent work actually looking at habitat units from LiDAR data. So habitat units are basically a human's way of simplifying a stream into 4 categories. So there's riffles. If you go down to the boardwalk by in the Redford Ravine, a lot of that is riffles. It's rocks with fast flowing water over it. We might have deep pools where salmon like to hang out, or cascades where there's a waterfall, or glides. I can't remember what a glide is. You can see those illustrated here. And essentially what we've done in this project is we've built a model using the LiDAR data to predict these 4 classes across our stream landscapes. And on the left, you can see what the LiDAR predicted, and on the right, you can see what we measured in the field. So now you can start to see we're getting where the streams are, we're getting how steep they are they accessible for fish, how wide are they, what kind of habitat units can we expect in them. And this kind of data is something that we've never had before, right? If you wanted to get this information, you'd have to send a crew out. If anybody's ever walked in a forested stream in British Columbia, especially on the coast, is a nightmare, right? Yeah.
I'm wondering if this data is like publicly posted, or if you have to pay the forestry company to use it. What's the process?
Yeah, that's a great question. So it depends. The data that would be available is just the raw LiDAR data. Like, companies are never going to do this. This is kind of research level at this point. If a company flies their own data and they pay for it, they have no obligation to provide it to us at all. But if the company gets any government funding, there was a court case in 2021 that decided that all of that LiDAR had to be open and free to the public. So all LiDAR data that has been acquired with public money at all is all available for download online. And that's how I got like that Vancouver LiDAR data. There's a big kind of government corporation weird thing called BC Timber Sales, and they fly a lot of LiDAR across the province. And that has all become available for us. And that's a huge source of data for us now in our lab, that we have this coverage across the province. And the province has actually committed to, I believe, by 2030, flying LiDAR across the entire province. That'll be the biggest acquisition of LiDAR data in the world in human history by about 3 times. So it is a huge project, but the provincial government obviously sees the value of doing that, and it's great for us as well. And hopefully you'll be on board as the taxpayers. Okay, so we can do things like take that stream and try to grow it outwards, using thresholds to try to figure out how wide our streams are. This is often a thing that fisheries biologists are interested in, because the width of a stream tells you a lot about what can live in that stream. So we've done some work with that as well. The final thing that we've done in the stream section, well, the final example I'm going to give you today is looking for wood. So dead wood is a really important resource for fish in streams. Dead wood will block a stream channel, will make more habitat, it will accumulate sediment and make a nice pool, and it basically adds complexity to a stream. It'll add food to a stream, and it'll add shelter for the fish. So wood is a super important part of streams, and we're often very concerned with how much wood is in them. If you go to somewhere like Sweden, they take all the wood out of the streams, and they turn it into pellets for their forest industry. BC luckily has a lot of protection for wood in streams, and in some cases we're actually putting wood into our streams, especially in the lower mainland where our streams are very degraded. They've lost a lot of their wood. They're now cutting down trees, putting them in the stream, and actually cabling and anchoring them in so they don't get washed out with the next atmospheric river or whatever. So long story short, wood is really important in streams. And so we tried to map it using LiDAR data, of course. So we take the point cloud of the forest, we do some fancy filtering to just get basically the stuff on the bottom. And then we basically looked for what we called linear features. So when there were points in a line, we detected all of those. We did some other fancy stuff that doesn't matter. And that gave us the wood in the streams, and it worked pretty well, especially when the logjam went across the stream. When it was up against the bank, it was quite difficult to obtain. But again, having an idea of now we know how wide it is it accessible for fish? We have a sense of how much wood is in the stream. It tells you a lot about the forest. And we can do that across a huge area, right? We don't have to send people to all these different streams to do checks. So super, super powerful, not only for vegetation and terrain, but actually for studying our streams. Yeah.
Did you go about tapping all this later? Because just like,
There, yeah, we built an algorithm, basically. Yeah. I can send you the paper if you're interested in the specifics, or it's right here. Okay. I had one more example I just pulled right before this talk. This is the Chilcotin River landslide. So there was LiDAR data collected before the landslide, and then this guy from UNBC flew it again this summer, and they basically calculated the change in the terrain to quantify how that landslide actually changed the watershed, right? So this was before the river broke through and restored itself, but at the time we didn't know if it was going to be a huge catastrophe or whatever. And the fact that you can just fly a plane up there and get this information really quick is super, super useful, and it's a great part of LiDAR data.
I have a question.
Yeah, Dan.
How long does it take to map area big of a size like this?
Like with an aircraft, you could fly this in 10, 30 minutes, something like that.
Oh,
The
wow.
plane will basically just go like this. I don't know exactly for this. It depends how low you fly and how much overlap you want, how dense you want the data. But if they were flying this for just like a standard forest, the plane would come across like this, come back like this, go once over like that, probably like 3 passes, and you'd have data over that whole area. And with the drone, it would probably take 500 meters. It'd probably be about an hour to cover that. Yeah. So not huge amounts of time when you consider sending people out to do this kind of surveying, how expensive that would be, how dangerous it would be for them, and how much they would actually be able to cover, right? Okay. Now let's talk a little bit about drones. So everything that I've shown you so far has been from satellites or from aircraft, and that has really been the foundation of remote sensing over the last 50, 60 years. We started with satellites, then we started putting things on aircraft, and now we have drones. And drones follow all the kind of same principles, spectral reflectance that I've been talking about. LiDAR is measuring all these points, but kind of imagine kicking the detail up thousands of times, and then also reducing the area that you can cover a lot, right? If you think about a Cessna, it's flying 2,000, 4,000 meters up in the air. It can see such a large area from up there. A drone in Canada, I'll talk about this more, but we're limited to about 100 meters, 120 meters. So you can cover a much smaller area with way, way, way higher detail. And you don't have to deal with clouds most of the time, which for satellites, clouds are a huge pain, and even for airplanes, they can be a huge pain. And you don't have to pay somebody to rent an aircraft that might crash, and lots of benefits. So regulations, this is always a fun topic, and I'm happy to chat more. There's a lot more regulations than I've included on this screen. But basically, you have to have a license if you want to fly any remotely piloted aerial system, which is what Transport Canada calls a drone, that's over 250 grams. So somebody thought about this, and they created this drone. Anybody have a guess how much this weighs? 249 grams. So As far as Transport Canada is concerned, this is not a drone. This is just a flying piece of plastic with a camera on it. So all these regulations only affect drones that are 1 gram or more heavier than this, just for reference. And you can take a look at this later. So all these drones that are greater than 250 that have to be registered. So the serial number is all with Transport Canada for this big one over here. You can't fly in controlled airspace unless you get special consent from Transport Canada. It's a huge pain. You have to keep drones in line of sight. This is a rule that Transport Canada has made for all drone use across the country. It's mostly aimed at like cinema, at realtors, at construction companies, flying in the city, you know. Unfortunately, this rule also technically applies to us in forestry, where I'm in, you know, northern Alberta flying a wildfire and there's nobody within 100 kilometers. Technically, I still have to keep it in a line of sight. In forests, this is very difficult, but we always do our best to comply with Transport Canada regulations. Any other questions about regulations? Yeah.
Your little drone,
Yeah.
how much sensing
Yeah. What can it?
equipment can you put on it?
Yeah. So the downside of this little drone is it just has a camera. So all this is going to be collecting is visible light. It can't collect any wavelengths beyond visible, and you can't change out the sensor that's on this thing. So it's only going to take photos, which is still super useful. But that's why this one is so good, and I'll talk about that a bit more when I show you this big drone, because it allows us to change out the sensor and collect all sorts of different information. Any other regulation questions? Okay. So can we fly at Still Creek? This map doesn't look good. Unfortunately, we're right at the edge of the Vancouver restriction area, which ends at Boundary Road, basically. So yes, we can fly at Still Creek, just Still Creek that's beyond Boundary Road. I think probably if I did the applications and everything, we might be able to get a permit to fly the ravine or something if we had a project for it. But legally, we could cross Boundary Road and we'd be totally fine. If we did it here, we would be fined for, it's only up to like $5,000. It's not that bad, but I'd like to avoid that if possible. Okay. Any other questions about drones so far?
Does that include the 249 ground ones?
It's very unclear. I say no.
Yeah.
Because Transport Canada doesn't regulate these drones.
Yeah.
But you know, you never really know with government regulations.
Nobody should be flying 100 meters up in anything bigger than drones. So.
Yeah, exactly. So yeah, it's a gray area, but I'm just assuming not for now, and I've never had a problem. Luckily, there's not many Transport Canada people wandering around Vancouver. Yeah, but it has happened. Any other regulation questions? Yeah.
Regulation. Well,
Yeah.
do you know why those boundaries are in
Yeah, so it depends. Some of them, like the YVR one, all airports in Canada, I think they have a 30 or 50 kilometer radius of just you can't fly anything within this area. And then jurisdictions can set their own. So like Vancouver has set one. This is probably the heliport or the float plane area. Vancouver just set a blanket one for the entire city. So I don't know exactly the process of filing for restricted airspace, but kind of seems like anybody can do it. So yeah.
That means City of Burnaby approves it.
It doesn't mean they approve it. It just means they don't restrict it. Yeah. So they don't have specific things saying you can't do it, therefore you can't. Yeah. And then so if anybody's ever interested in getting a license, if you are Canadian or you have PR, it's super easy. It's like a multiple choice thing. It'll probably take a few hours and it's like $50. So if you ever want to fly over 250 grams, get a license. Yeah, there's no expiration at this point, but it's such a new thing they might make them expire sometimes. Yeah.
Obviously this is a bit tongue in cheek talking about
Yeah.
but given that, like you're saying, that the best use for the drones is on these vast areas where it's difficult to access on foot.
Yeah.
Obviously, what rental moving isn't like that? Would there be any advantage in doing any sort of drone screening of rental moving that you wouldn't get just by looking at it?
Yeah, I mean, the ravine is super hard to access, even though it's right there. and it's not particularly remote. It's covered in vegetation. The cliffs are super steep. Like even for the stewardship stuff, there's only a few areas where you can really safely do work. So the benefit of a drone would be you could cover that whole area that you can access, and it would give you a lot finer resolution to go away and do things like try to map the invasive species or try to look at the very detailed stream morphology to figure out where the banks are, how much wood there is, and that kind of stuff. So yeah, there could be a lot of benefit to flying the ravine. Any other questions?
So you get some sort of special permit to fly in the restrictions?
Yeah.
Because I saw a drone just Monday.
Yeah.
That looks a hell of a lot.
Yeah.
Well, on Main Street and 20th Avenue.
Yeah, you can get applications. It's a lot easier if you're like in, you know, Vancouver film industry or something and they have push with the government. If you're just some Joe Schmo and you want to fly the ravine, you could apply for it. But we've done some applications actually around YVR where we were doing some projects looking at the mud flats. And some of them got approved and some of them didn't get approved. So we try to just not do research where there's restrictions because you never know who's going to be approving the permits that day. And it's hard to build projects when they're in place. But yeah, like if you saw one, and also you can fly and break these rules and probably nobody's going to catch you or do anything. So like if you go to the fireworks in the summertime, you'll see probably about 6 or 8 of these things up there. I really doubt that they have like up at night, flying over people, like yeah. So yeah, and a lot of people have drones over 250 grams that they're flying, you know, all the time on vacation and stuff. So, but these are the rules. Okay. Yeah.
With a drone like that, how far can it be from the person?
That's a good question. So,
I guess for both of us.
yeah. So technically, it has to be within line of sight legally, assuming
A very long line of sight.
assuming you have very good eyesight. I've flown this one about 3 kilometers away. Yeah, so you can cover a huge area. And this one I've flown, I think it stops you at 1.5K or something, 2K. But technically it could go a lot farther. It uses radio waves, which are a very long wavelength and they can travel super far, as you know, if you've used a car with a radio. So yeah, they work super well. It totally depends on the terrain though. Like if you're at the bottom of a mountain, you try to fly over that mountain, you have no luck, right? The waves will be blocked. If there's really tall trees that can block it, but if you're in the prairie or something, you could fly. I think the manual says up to 20 kilometers. At that point, the battery would be running out and you wouldn't be able to get back. But yeah, technically you can fly very far. So you can imagine someday when if these restrictions ever change, you fly a lot higher, you can fly a lot farther, you could have multiple of these in the air, and that just helps cover a lot more area with this kind of data. Okay, so now we can see some actual drone data, and we'll talk a little, and that's where my PhD research comes in. So I don't work with streams, unfortunately. I worked with them in previous schooling, but could get funding from streams, so I work in forestry. And my project is really centered around how we can use these kind of drone remote sensing technologies to essentially improve the way that we're monitoring and managing our forests. I want to be able to monitor the growth of our forests to see if they're coming back, how fast they're coming back, and also be able to tell what kind of species are coming back. Are we planting something and is it dying and something else is coming back? Are we planting something and it's kind of stagnating? Is it going exactly as we expected? Drones are really useful because they allow us to go out to a forest stand and check in on how it's doing. And that's where my research comes in. And also I'm interested in using drones to monitor the effects of kind of alternative forestry practices, aka things that are not just clear cutting. So I'll show a few pictures of that. Yeah.
So you're saying this works for trying to evaluate like a shelterwood regen system or something, or you can look under the large retained trees to
yeah, exactly. Because you can this is drone LiDAR data now. And you can just see the sheer amount of points, right? We can see all those trees in the understory. So yeah, there's a lot of potential for that. Yeah.
I've been kind of sitting on this question because it felt really dumb, but how do you get data points underneath other data points? Like if it works with light?
Yeah. So basically it shoots a pulse of photons, which are just bits of light that's about like this. And some of those photons travel, and maybe there's a branch here, and they return, and some of them keep going, and they hit another branch and they return, and some of them keep going and they'll hit the ground and they'll return. So one pulse of light will be many photons, and you can actually get multiple points for every pulse. And it's also firing, this one does about 240,000 pulses of light per second. And so even though there's leaves and vegetation and stuff, there's enough little gaps. If you've been in the forest, even when it's quite dense, there's still light, right? It's not pitch black. And if there's light, that means light can pass through from above, and that means lasers can pass through a LiDAR. Yeah.
So would you expect the understory to be lower resolution data than the canopy?
Yeah, there will definitely be more points in the top of the canopy than down below.
And something like the riverbed where it's going through water and then hitting the ground, is that all handled? Like, does the software is it able to recognize the fact that the light is hitting water?
No. Yeah, so that's a big issue, especially because, let's see if this is worth it. If we return to, this PowerPoint is like 1.5 gigabytes with all these GIFs, so it takes a second. But if we go back to almost there.
Should have asked this sooner.
No, it's okay. Okay, so the problem with water, so these are our two water surfaces here, right? We have clear water and then turbid water. That just means there's silt and mud and stuff in it. And if you look, this is the visible. If you look, there's maybe a little peak around here, which is kind of why it's bluey green. But then you see this steep drop off, right? And the lasers that we use for LiDAR, they shoot wavelengths right here.
Okay.
So what that means is when one of the laser hits water, it's completely absorbed. Water doesn't reflect any light from the laser, maybe a little bit, but that's a huge problem for LiDAR, is when it hits water, it's gone. There's nothing to return to the sensor, so you can't get points on water unless there's a lily pad or a log or like something. In reality, if there's really shallow water, you can get some points. There's some specialized LiDARs that actually use a laser in this wavelength, and that's called a bathymetric LiDAR. It lets you map like kind of shallow water. It works a lot better. But we're always using lasers from here because they're collected for forestry. So yeah, it's super hard when you get, the farther you get down and the taller the canopy is, the harder it gets to like see stuff beneath the canopy.
But you had really, like you had the ravine, like the riverbed of the ravine.
Yeah. There's just like enough points, I guess, that it looks good. But if we wanted to go away and do our fancy things that we've been doing, it might not work so well.
Right.
Yeah.
Actually, that's a great segue, because that's gonna ask you, could you use either two different kind of lasers or microwave or something of the same drone?
Yeah, so we don't, so that's called multispectral LiDAR. And it's this idea that you can have multiple lasers shooting multiple wavelengths at the same time. And so there are people doing that. There's one person at University of Lethbridge who owns one of those units. They're very expensive and experimental. And you get problems because the lasers have to be kind of spaced apart a bit.
Right.
So it's hard to match a point up that's been collected from a different angle. Anyway, the data is a nightmare. It can be done. If you ask the guy at University of Lethbridge who has it, he'll tell you it'll do everything. We've had mixed results, but yeah, that's kind of where things are heading. Yeah.
Related question: anybody who watches Specsavers ads, they talk about optical coherence tomography.
Okay.
To basically match the retina and can map the depth.
Okay.
And it's not using coherent light. So if you do a pulse of really bright, non-coherent light, you see what you get with different reflections of different frequencies.
I don't know what coherent and non-coherent light means, to be honest. Is that like a...
Oh, coherent is laser, non-coherent is just light.
Okay. I'm not sure. I don't think I'm qualified to answer that. Okay. Okay. Let me just do this so this is faster. Okay. Okay. So on to a bit of my PhD research. So quick summary, since we talked about this 5 minutes ago, I'm trying to monitor growth and species of our forest coming back and look at the effects of different forestry practices. So we can start out with, this is a vegetation model, just like I had for the ravine, that white and black image, but this is for a big forested area. I fly these areas before they do any kind of harvesting, and then I fly them after they've done the harvesting. So here they've done something called a thinning. And the thinning, you're not cutting all the trees, you're going in and bringing a machine and you're cutting these rows and you're removing some trees in between the rows. And what that does is it lets those trees that you leave grow better and faster and have more water and less kind of competition. And you also kind of get some wood by taking those trees out. So it's kind of a win-win. Problem is it's very expensive to do because we're used to just clear cutting huge areas, making tons of money. This is a lot more costly. And because of that, there's very little assessment done of these kind of things after they do it, if they even do it at all. So a big part of my project is made to basically see how we can assess a commercial thin using this kind of data and using RGB data collected from the drone. And so this is just a very small area sample of my data set. I have sites all across the province that I've been flying over the last few years before they do any harvesting and after. Here's another example we have, and you can see how the resolution, think about that Landsat image we had with the ravine, it looked really blurry. Now we're getting to, that was a 30-meter pixel. So every 30 meters we have a value. Now we're working with 1 centimeter pixels, right? So think how small a centimeter is. I have RGB measurements for every single centimeter and multispectral stuff for some other stuff. So it is just a crazy amount of data. My poor computer works very hard. Yeah.
Is it easier for you to interpret the data in a mixed species stand because it doesn't look as uniform in the image?
Mixed species stands are always more difficult because there's a lot more variables. Pretty much all the stands I work in are mixed species, mostly Douglas fir and spruce and washable pine. But yeah, you can see
Sort of size area is this, and you just like this area is, are we in the
No.
area forward?
I've just zoomed into a little spot. So this is probably about, we use hectares in forestry. A hectare is about 2.5 acres. This is probably about 1 or 2 hectares. I have this kind of data for thousands of hectares across the province. So a lot of flying all from this thing. Yeah.
You mentioned multispectral, but the laser you're using is only one wavelength, right?
Yeah, exactly.
So how are you getting the colors then?
That's a great question. So all of this is from the LiDAR. All of this is from camera. They put a camera on the LiDAR. So it's flying, it's collecting LiDAR pulses. It's also taking photos every single time, every second or 2 seconds. So you get kind of both data sets at once. And then that's only RGB data. So that's only visible wavelengths. If we want something outside of the visible, we have to use a very specialized camera, which I'll try not to break, like this. So each one of these 10 cameras will see a different wavelength across the EMS. So the camera on that thing only sees RGB, also has the LiDAR. Each one of these is a different wavelength. So these cameras were developed for agriculture because people wanted to see whether their crops were healthy or not, or if they have disease. And we've been using them a lot for telling the different tree species, telling if they're drought stressed, those kind of things. So that's where this comes in super handy. But you need a very special tool for that. And right now, if you want this combined with a LiDAR, it's like a lot of money, hundreds of thousands of dollars. But a few years ago, the LiDAR itself was like $200-300 grand, and now it's 15,000. So the cost is really dropping as these things get out. Yeah, Joe?
And that's a lot more data.
Yeah, exactly. It's a lot more data. You get 10 bands of information instead of 3, right? So data is a blessing and a curse in some ways, especially when you're trying to finish your PhD. Okay, I have a few more slides. So yeah, we got pre-post for thinning. And the other project that I'm doing, I'm monitoring growth. And the way that I monitor growth is I take multiple LiDAR acquisitions. So the first one you can see when the trees are short, that was in 2018. The second one was in 2020, and the third one was in 2023. The first 2 are from an airplane, and the last one is from a drone. So in my project, I'm working on combining the LiDAR that we get from airplanes with the LiDAR that we get from drones to actually look at each tree and see how it's growing, what species is it, And that can tell us a lot about how the forest is doing, and it can tell us a lot about kind of dynamics about how the forest grows that we've never known before, that we've never been able to measure when you just go out, okay, let's do a plot here, measure some trees, and then go back to the truck, right? You get information across huge areas of more or less all the trees, and you can get how much they're growing and what species they are. You can look at the terrain beneath them and see what kind of sites they're on. So from a forestry perspective, it gets very interesting. Yeah.
Do you think that it's valuable to do this sort of thing in an urban forest context where you might have, I mean, let's say you're doing Stanley Park,
Yeah.
so a large park for an urban scale,
Yeah,
compared to doing ground survey?
I think so. Like, especially, let's take the big hemlock looper or whatever the disease, looper moth they had in Stanley Park. If you collect LiDAR data before that and then after, you can actually have a real concrete idea of how many trees died, how many trees fell down, that kind of stuff that you're not going to get if you just go in Stanley Park and do 100 plots or 1,000 plots, right?
And is it more cost effective than sending people out to do high plots?
I mean, from a cost perspective for Vancouver, they're already flying it anyway, right? So in some ways it's free. It's like a value added to whatever they're doing, right? So I think so, yeah.
Is that a really tall tree there?
Yeah, that's one really big tall white pine that they left, and all these other ones have been planted.
Oh.
And so we can look at some other area. Here's some, you can start to see trees actually falling over if you look where the points are. So it not only tells us how much the trees are growing, it tells us whether they're dying and whether they're falling over. And so what I do is I detect as many trees as I can using a bunch of algorithms across the forest. So each one of these points is a tree that I've detected. I've used data from this fancy 10-band multispectral camera to basically classify which species they are. In Ontario, there's a lot more species than we have, which makes it extra fun. And so now we have each point is a tree. We have a sense of what species it is. And we can look at those 3 LiDAR data sets and say, how much is it growing in terms of meters per year, right? So the darker blue ones are not growing very much. The yellow ones are growing a lot. And so what I do in my research is I say, okay, these red dots are pine trees. Are the pines growing faster than the spruce? Are the pines growing faster on certain sites and not others? You can start to ask kind of unlimited questions once you get these really, really rich data sets, which hopefully will reveal something useful to help us monitor our forest better. Yeah.
Can you give an example of the specific data you get from the waves that are outside of the visible light? I really hard to imagine, like, what kind of stuff does it tell you? Does it give you more accurate?
So I'm going to scroll back to your favorite slide to answer that question. And I should have included this specifically. So visible light's here again. This is everything beyond the visible. This is called the near infrared, right here where I have my little laser. This tells us a lot about the health of the vegetation. Basically, because, without getting too complicated, because of how the cell structure of a leaf, if it has a nice healthy structure with good strong cells, it'll reflect a lot of near infrared light. If it's degraded, if it's the fall time and the leaves are senescing or they're losing their resources, it'll break down and it will reflect less. So, for example, near infrared light is often used for vegetation health. Or in agricultural applied fields, they'll look at the ratio of how green something is versus how near infrared it is, and that'll tell you a lot about how healthy the plant or the field or the forest is. So that's one example. The farther you get over here, you can see, let's take the dry soil and the wet soil for an example. When you get into the longer wavelengths, water is really affecting this. So that's why we see a decrease in reflectance, especially for snow and ice versus clouds. So this tells us a lot about the moisture content of something. In the visible, it tells us a lot about the different pigments that are in the leaves. So you can basically look at different sections, and there's a paper for anything you could imagine to look at the different ratios to tell you something useful about what you're looking at. Yeah.
Is the data to determine the species of plant,
Yeah.
is that open source, or is that something you have to purchase like a license?
I flew that data with the drone, but I collected that data myself.
Okay, so you collected the data, and then, but like in terms of knowing
the spectral
Yeah.
signature of a given species.
Yeah.
You calculated that based off?
That's a great question. Yeah, so there are kind of free, they'll call them spectral libraries, where people will collect the signatures. So these are signatures. They'll collect them of 100 species and 1,000 individuals, and they'll upload that open source so you can use it. The way that I do it in mine is I go in the field and I locate thousands of trees and I tell what species they are and how big they are, and then I connect those with the data that I collect from the drone, and I use machine learning to predict the different species based on the relationships that I know. Does that make
You're
sense?
building your own
Building your own,
relationships,
yeah.
then
Yeah,
you can field research, you would touch the tree and say that is.
yeah. This is a black spruce. I know it's a black spruce.
Cool.
I tell my model that, and it looks for patterns to find similar curves, and then it says they're black spruce too. Yeah.
So are there also signatures available if you wanted to like quickly pinpoint white pine blister rust or like Swiss needle cast or something just from a quick scan, where you can just go, okay, this is what's going on from a health perspective?
Not yet. Health is very hard. Depends a lot on genetics. It depends a lot on the weather of that day. Are there clouds out? Is it a bright sunny day? What time of day it is? All of that affects these kind of relationships. So when you get to something really subtle like health, it's way less consistent than doing something like species, where there are pretty consistent differences no matter what the conditions are. But health is kind of one of the holy grails of remote sensing, we like to say, and a lot of people are trying, and some people have success, but there's certainly no quick solution to do a quick scan yet. Yeah.
Can you access community status of the forest?
Yeah, totally. So the way that we do that is we use a thermal camera. So basically, when plants photosynthesize, they emit water moisture through the process of respiration, and so that'll cool down the leaf. And so if you have a thermal camera, and you can't, thermal is not on here, it's even farther off to the right side of this graph. But if you look at the thermal signature, it tells you a lot about how much water that plant is emitting, and that tells us a lot about drought stress. So we do a lot of work on the coast looking at genetic trials to see which trees are doing well in a drought event, which trees are doing poorly, and we use thermal for all of that stuff. Okay, great questions. I didn't expect you guys to know so much. No offense. Okay. Okay, cool. I only have like 2 more slides, and then we can look at the drones. Okay. Oh, I literally have one left. And it's a little video of us setting up the drone in the field. We bring our truck up, we set up the generator to charge the batteries, we bring the drone out, we put the sensors on. Nowadays, we even have Starlink and stuff to have internet.
You'll be good where I'm
You should tilt the, tilt shift.
What's that?
You should tilt shift the video.
from.
Make it look a miniature.
Oh yeah, that'd be cool. Yeah, so this, it looks glamorous, but if things are going well, you spend just hours and hours sitting out in the field, and the drone comes back, 30 minutes later, you put in new batteries, and it keeps taking photos and scanning LiDAR data over these huge areas.
Did you film this with the drone?
Yes, this was filmed. Yeah.
So are you mostly just programming and afterwards?
Exactly. So what I'll do is I'll say, okay, this is my big forest area. I'll set parameters like how high I want the drone to fly, how fast I want it to fly, how much overlap I want in the images. And the drone will go up, it'll use its GPS, and it'll follow that. It'll go like this, flying a grid, taking thousands and thousands and thousands of photos. And those are all stitched together into the things that you've seen in the last slides. Yeah.
What is this for the data?
It just has SD cards on, just like a camera. So another thing not pictured here is taking out the SD cards. I have this case that has like 20 different SD cards in it, and I'm just constantly backing up my data and
Old-time slideshows.
Yeah.
Insane amounts of data.
yeah. It's a bit of a nightmare.
Do you have experience with losing data? Or you don't want to talk about that?
I have never really had a catastrophic loss. I have had the drone crash. actually, which was near this area. One of the motors failed and it just fell right out of the sky. I was walking along looking at it, and all of a sudden I just saw leaves. But the drone was totally fine. One of the motors failed, and it actually can adjust the other three to be able to slow itself down so it doesn't just plump into the ground. And it landed in a nice soft balsam fir tree that kind of like the hand of God reached from this and saved it. And the drone was fine. The motor didn't work, but yeah, no issue.
So is it live streaming video then?
Yeah. Yeah. So this seems like a good time to. I'm going to turn this thing on. It's not going to take off. FPV is a different kind of drone that has a. 1 second. An FPV. Yeah, you have a goggle system, and you actually control all of the rotors and how fast they're turning. So we have one person in our lab who uses those for urban trees, and he does these crazy corkscrew patterns and reconstructs the tree. But operationally, there's not much use for those unless you're fighting a war or something. Okay, cool. So is this a good place to do this?
Yeah, it looks like this leg is just on the edge of the thing. Yeah. Go for it.
Can you go me? Yeah, can you do that for me, please? Thank you. Okay. So I would love if we could do an actual demo of this thing and fly it, but in lieu of that, I'm just going to turn it on and I'm going to talk about all the different components. So this is the controller. This is the thing that communicates with the drone at all times. You can see it start to come alive. I didn't even introduce the drone. This is Loretta. Loretta has, I think, last time I checked, about 8,000 kilometers of flying. I think about close to 900 hours up in the air. So she's going to California this Christmas to be serviced. They're going to replace all her motors. So we wish DJI. This is a DJI Matrice 300. Let me just turn off the lighting music. Okay, so a quick thing about like drone manufacturers. There's this company DJI, which probably most of you have heard of. It's from China, and they're extremely far ahead. They control about 80% of the market, mostly because they started 20 years earlier than anyone else, and they have a lot of support. So most of the stuff we use is DJI. On the drone right now, I have this LiDAR sensor. So what you can see here, right down here, there's an RGB camera. So all those images that we captured are from this little camera here. Up here is where the LiDAR is actually. So behind this, there's a laser shooting the pulses. And then those photons are coming back, hitting the sensor, and it's recording the returns. And it's mounted on this gimbal here. So this actually has a few ways to stabilize it. Because when the drone is flying in the real world, it's going, and it's constantly shifting around. But the gimbals actually allow the device to stay relatively stable and, importantly, always pointing directly downward. Has a lot of other cool features, including a camera on the front. So when I'm flying, I can always see what's in front of me, and I can see what's below me. It has a bunch of obstacle avoidance sensors on this thing. So all these little things that look like cameras, they're basically little sensors just like in your car. If you have a newer car, when it beeps, if you're going to back into the parking space or something. Same kind of idea, but it has them on the top, on the bottom, and on all the sides. It's called omnidirectional obstacle avoidance. So if you fly close to a tree, in theory, it'll detect that tree and it'll stop, or it'll try to go around it depending on the programmed in.
In theory?
Yeah, well, I've never had it not do that, but I wouldn't go around testing it with my boss's one at least. You can kind of see us on the front-facing camera here. I tried really hard to rig this up to this projector, but it didn't work. So, but we'll have some time to take a look after. And I can switch to the LiDAR camera as well here. You can see I can do things like control the tilt, right? The laser on this, it says right here, it's a class 1 laser product. So it's actually technically even less dangerous than this thing. And that's because it emits near-infrared light. Your eyes can't see it. So if you're all fine, I will do a LiDAR scan of you right now. If there's an objection, unless if people are afraid of like Wi-Fi and stuff. But okay, what else? So on this thing, I can plan my routes. So the way that that works is I program in an area and it makes an automatic flight plan based on how high I'm flying. I can do something really useful, which is I can take an elevation model like I've shown you, basically like this, and I can program it into the drone. And what that'll do is it'll make the drone maintain a constant elevation, right? So if we have a hill like this, and we set our target at 100 meters, it's going to come at 100 meters, it's going to go up as that hill starts, it's going to go down as the hill drops. And that really helps for having a consistent data product at the end. Otherwise you have gaps or too dense or hit a tree or something. It has a giant station, which you can see in this video, if the video plays again. It has this big tripod with this big antenna with this big thing unit on the top. That's called the RTK base station. And that is constantly communicating with the drone through these antenna. And it basically means it's like a really, really well known fixed point that every single picture and every single LiDAR pulse that this captures is referenced to that. So that means if it's a kilometer away collecting points or it's 5 meters away, it's all going to be relatively referenced really well. So in the old days, they had to go out and put these things called ground control points, which were like big red X's where you measured the location and you used it to like rework everything. Nowadays, we don't have to do any of that, which is fantastic. And so the reason that this drone is so useful is because we have this gimbal mount. We can swap off the LiDAR. We can put on a multispectral camera. We can put on the thermal camera. Nowadays, they even have this thing called a dual gimbal mount. So you can put 2 units on at once. So we could be flying the LiDAR, taking RGB photos, taking multispectral photos. And the other thing that's great about this is the big honking batteries. So just take one of these out. The batteries last about 30 to 40 minutes per set. That'll depend on the wind speed, it'll depend on the temperature, it'll depend how high and fast you're flying. But they're actually quite heavy, you can feel them afterwards. And they're quite expensive, these are about $1,000 a piece. But the nice thing is, it'll fly for 40 minutes, it'll come down and land. I can take out one battery, and I can hot swap. So the thing doesn't even have to turn off. I can put in a new battery, put in a new set, and it'll take off and return right to where it stopped and keep going. So it really allows you to cover huge areas really efficiently without having to restart the whole system every time you need to change your battery. Also, with the gas generators work incredibly well. Love solar panels, but they don't work for this yet because just the sheer amount of energy this thing needs. But we can run a gas generator out there and recharge faster than we're actually using them. So sometimes I've started before the sun even rises and I finished it dark, and it allows us to cover huge areas with these kind of systems. Okay,
How much did you say that this whole set actually was?
Great question.
With all the pieces and everything.
So get your shopping list out. The drone, just the drone, no cameras, no sensors, no base station, is about 12.5, 15 grand, plus inflation probably now, everything's 20% more. The LiDAR unit is about 15, 12 grand as well. The base station is about 5 grand, the battery is about $1,000. So the number I like to say these days is about 50 grand for like a full, 50 to 30 grand for like a full setup, which sounds like a lot of money, but I mean a house here is what, $5 million. And paying people to go out and survey is so expensive, right? You have to pay for their hotel, for the truck, you gotta pay for each of them. Somebody hurts their back, that could be $1 million, right? So when I tell the provincial government that's 30 grand or 50 grand, they kind of laugh at me at this point. So that's your tax money, but yeah.
What you mentioned, like going from dawn to dusk. What's sort of the amount of acreage that you can?
Yeah, so my biggest day, I think I've covered about 1,200 hectares, so that'd be about 4,000 acres. Yeah, that was a big day. But it depends how fast you fly, how high you fly. You could probably push that number to 2,000 or 3,000.
Does the fidelity match the speed? Like if you're flying too fast, you might not get the same resolution?
Yeah, so if you think about it, it's constantly recording points, right? If I'm moving slower and I'm collecting points, I'm going to get a lot more points. If I'm moving fast, my point density, the number of points I have for every meter, is going to drop.
Is there a standard that you have to adhere to, or is it based off?
Well, the problem is this thing is like 2 or 3 years old, So there was no standard when I started, so I went out to the forest and I tried a bunch of different altitudes and speeds, and I found one that I liked. And
So
I
you're
stuck
setting
with
the
that.
standard now.
Yeah, exactly. I have this. I do 80 meters at 6 meters per second. If you must have. Now after 2 or 3 years, there's been a bunch of papers. People do 100 different sets and compare them all. Yeah.
Speaking of standards, I noticed there wasn't a rover in your kind of grocery list of stuff. Are you doing independent checkpoints on these during surveys?
Yeah. You mean for like?
By RTK or total station for treetops, things like that?
Yeah, we just use the RTK base station.
Just a single base station,
Yeah.
or you're not going all the way
No, because a lot of time you can't. In the forest, especially in forestry, you might get access to one small point, but it might be kilometers of walking in, or there might be no access at all, right? So, and it works well enough that we don't. Are you a surveyor, or do you have a surveying background? Okay, cool. Yeah, like depending on the application, people have different expectations of accuracy.
Yeah, like we wouldn't accept anything without this checkpoint.
Exactly, but in forestry, we have no alternative. So even if it's plus or minus tens of centimeters, we don't care.
So in
Right?
forestry, like before that stuff, we would try to shoot treetops, stuff like that, with total station. You guys even have access to one of those? Or?
We do, but they're so heavy and cumbersome that you can't bring them in like effectively to do anything. Yeah.
I'm curious if you ever have any issues with birds,
That's a
or
great
been trying
question.
to stay away.
I have had issues with birds.
Okay.
So most commonly I'll have ravens. And ravens have never caused me any problems, but they just make me nervous because they're so curious and they'll fly around cawing. They'll fly around the drone. I've had red-tailed hawks take an interest, but the only real problem I've had was with a bird called an American goshawk. Some people might be familiar with it. They're known as the most aggressive bird in North America, particularly when they're nesting. And I unknowingly took the drone off close enough to the nest that when I was landing, and the goshawk came right out of the bushes, and it was like, and luckily I was paying enough attention that I just shot the drone right back up, and I landed like several hundred meters to the road. Thankfully I'm a birder as well, so I knew the goshawk and I had interactions with them before. But yeah, people have a lot of problems, especially in the US, with red-tailed hawks. And at YVR, sometimes you'll actually see the falconers using their hawks to like control the airspace. So if some person is trying to take photos of the drone with one of these things, they can send the Cooper's hawk or whatever to go take it out of the sky, which is cool. Any other questions?
Even like in military contexts, I think I've heard of like birds of prey being used to take care
Yeah,
of
it's super cool, right? Yeah. Birds work, right? They're the original drone.
Yeah.
No battery required.
There's millions of years ago.
Yeah. Did you have a question in the back?
Sure, yeah, I was wondering, are there many different companies producing the actual sensors? Like you buy the sensor separate, so
Yeah.
is that like a separate company, and
That's a
are
great
there
question.
many different?
Yeah, so most of the sensors we use are made by DJI, and the reason that we do that is because they're the cheapest and they integrate really well with this whole system. So when I plug this thing in, I can see, when I'm in the field flying the LiDAR, I can actually see the points coming in real time, I can see the images. This special system here is not made by DJI. You can tell by the fact that it has exposed wires and open ports, so it's not waterproof in the slightest. And you have no ability to control it from this thing. I have to actually bring a laptop out. This thing puts off a Wi-Fi signal that you connect to, and you have to turn the camera on with the laptop. And this is made by a company called MicaSense that just got bought by some other company. So there's tons of companies selling different sensors. Unfortunately, at this stage, most of them are way more expensive and they work worse than the DJI ones, unless you want like really high accuracy, like for surveying. Then those really $300,000, $500,000 LiDARs are necessary, but in forestry we don't really need that. Yeah.
Do you ever fly this in the winter? And if so, what challenges does snow and ice present?
That's a great question. So I have flown in winter. I try to avoid it because all the LiDAR gives us is points, right? So we don't really have any way to know if we hit snow or if we hit the tree. So if the trees are covered with, let's say 30 centimeters of snow, that is basically going to add that to the tree height that we think. And if the ground has a meter of snow on it, then we're only going to get the surface of the snowpack. we're not going to be able to like penetrate through and see the actual ground. So snow is not ideal because it kind of, distorts the reality in the data set that we get. Another issue is the batteries have to be a certain temperature to be able to be used. This thing can actually heat them up. So I put them in at like -10°C, and then it has to sit there for like 10 minutes warming them up, and it uses half the battery doing that. So I'll actually have like hand warmers, and I'll bring a big jacket and I'll like stick them in there, and like, I'll kind of nurse them. Yeah, winter is certainly challenging. Technically, this thing is waterproof too. It has about the same waterproof rating as your iPhone. And I have flown it in some pretty crazy rain, but you get problems, right? Because if you have raindrops in the air, it's absorbing all those laser beams, you get noise. And then Loretta has been flying for 900 hours, so all those waterproof seals are constantly bumping around, and I don't trust it anymore in heavy rain. But yeah, weather is, and the other weather concern is wind, right? If the trees are super windy, they're going like this, right? And if you're shooting LiDAR pulses, it doesn't know that the tree is moving, right? It's just going to collect information. So a tree that's supposed to look like this is going to be like wide. So a lot of the time you want ideal weather, but you drive out to the middle of the forest and you don't have a choice. Like my boss is not going to let me come back to Vancouver and go next week, so you kind of deal with the weather you get a lot of the time.
How many years have you had Loretta for?
Loretta has been with us for 2.5 years. Yeah.
What's the limitations that you find with your research? Like, is it the man hours of flying the drone, or like the cost, or like the man hours of analyzing the data, or storing the data?
It's getting people that know enough about like the background and know enough about computers to be able to handle terabytes of data, that have access to compute to be able to turn it into something useful. A big problem I have a lot is I'll show these beautiful point clouds, and people will be like, oh, I see the trees, like, can you give me this, can you give me this, can you give me this? But actually turning that into a product that you can give them versus seeing it in a picture is, years of work. So the big problem with the drone stuff is it's just so new, like it's like 2, 3, 4, 5 years. Basically they've been mainstream, and the LiDAR stuff even fewer years. So there's not many methods I can like go look up. I kind of have to just try things.
Have you started playing with AI to do the analysis?
Yeah, so we have a couple students in our lab specifically using deep learning. One of them is focused on predicting tree species just from the point cloud. So not looking at that spectral signature at all, just looking at the structure of the trees. Because let's say a pine tree usually grows out radially like this. A spruce tree is usually like a cone. Can we use deep learning to like find those kind of differences to classify species? It's had mixed success so far, but stay tuned for that. But yeah, lots of interesting AI and stuff. However, we have run into some trouble with AI and things because the government's all worried about AI research. Is it a security risk and that kind of stuff? So we're actually starting to trend away from using the word AI. But yeah.
You were showing that other sensor, and you were a bit late. So what was that like?
Oh, this one here?
Yeah, that other one. Like, what type of sensor is that?
Yeah,
one?
so this is called a multispectral system. It has 10 separate cameras, and each one of them captures a different wavelength of light. So 3 of them will capture red, green, blue visual light like we see. There's also near infrared and infrared and shortwave infrared wavelengths that will capture beyond that.
Yeah, and was that the one you were using for the identifying the tree species?
The tree species I get from this camera system. Yeah. Okay, anybody else have questions? You have a question? You look like you have questions.
I want to take a look at them.
Yeah, of course. Yeah.
Because you can use LiDAR for like underwater, right? Like,
Yeah.
Like I'm just wondering if someone also like does research for like underwater.
Yeah.
So if they use a pro-location or
Yeah.
there are some sensors.
They use sonar. Yeah.
Sonar.
So
on a
like,
drone, yeah.
if you not on a drone, well, they what do they call them? Remotely operated underwater vehicles or something. They're basically drones but underwater. Most of them have to be attached with a cable, and a lot of the time they'll actually use like a manned submersible with a sonar on it, or just use it from a ship. I don't know a ton about sonar, but if you go on Google Maps and you turn on satellite view and you go to the ocean, you can see all the ridges and all that kind of stuff, and that's all from sonar data. Yeah.
So I'd heard that you can create point clouds similar to LiDAR, but using a bunch of different photos.
Yeah.
Is there a big quality difference between what you can produce with LiDAR versus with that approach?
Yeah, so that's great you mentioned that. I actually cut that from the PowerPoint because I thought I had too much stuff. So they're describing a process, it's called digital aerial photogrammetry. So you can build up a point cloud by taking a bunch of photos, and if those photos overlap enough, we can basically see, imagine my water bottle is a tree. If I take a photo here, I can see the water bottle. If I take a photo here, I can see the water bottle. If I take a photo here, I can see it. Here, I can see it. If I do that a bunch of times, I can see it from a bunch of angles, and I know where the photos came from, so I can actually reconstruct a point cloud that looks very similar to LiDAR data, but just from pictures. The issues with that, the biggest issue is that you're never going to penetrate any kind of vegetation. So if we did that over the ravine, we get a beautiful surface of the tops of the trees, but it wouldn't tell us anything about the stream unless we had like a big opening in the canopy. That's kind of the biggest limitation. Otherwise, if you have weird weather, like if you have a sunny, bright day with clouds coming through, the shadows are going to be changing and the light's going to be changing. Sometimes it just doesn't work. It has to be like consistent enough that you can find common points in the images. That's called DAP if anybody wants to do reading later. Okay. Any other questions? Okay, so I'll be around for a bit longer if people want to come have a look-see.
Can we still LiDAR ourselves?
Can we put LiDAR again?
It can't work unless it has the base station. So I forgot that.
Oh.
Okay.